Hello everyone. In this video lecture, we'll be starting with the third module for the subject EC405 Optical Communication in the KTU syllabus for Electronics and Communication Engineering. So this is the syllabus for the fourth module for EC405 Optical Communication. So first one, optical detectors, second one, types and characteristics, third, structure and working of pin and avalanche photodiode, then noise and detectors, comparison of performance, optical receivers, ideal photo receiver, and quantum limit of detection. So we'll be dealing with each of these topics. So these are the frequently asked questions, the questions that has been asked in the last university exams of EC 405. Okay, to start with the third module, we'll go to the basics first. So in the previous modules or the previous sessions, we have learned about what is optical communication, what are the different blocks that come in an optical communication system. We have a transmitter, we have an optical fiber as a communication medium, and we have a receiver. And we have learned about what are the different types of fiber, how the fiber is manufactured. Then we learned about different optical transmitters, what are the different optical sources. That all we have seen and discussed. So here we'll be learning in detail about the optical receivers. Okay, what is an optical receiver? What is the function of an optical receiver? As you all know, we get the input as light in the optical receiver. So the function of the optical receiver is to convert this light back to the form in which it was transmitted at the input side. Normally, the light is being converted into electrical signal, because at the transmitter side we have the input as electric signal, and that electric signal is converted into light, and this light is being propagated through our optical fiber, and that we receive at a receiver. So the function of the receiver is to convert this optical signal back to electrical form. Okay, so an optical detector has many components. An optical receiver has many components in it, so like the amplifiers, signal conditioning circuits, things like that. So a detector, an optical detector, is a fundamental component in a optical receiver. Okay, we have an optical receiver. This optical receiver has amplifiers, signal conditioning circuits, and optical detectors. So this optical detector is one of the important part in the receiver. Okay, so again summing up, the function of the receiver is to convert the light signal to electrical signal, and this converted electric signal should be proportional to the light that is being coming inside the receiver. Okay. So when a communication engineer is designing a system, there are certain criteria he'll be following when he is selecting the optical receiver. So first criteria is the size of the optical receiver should be compatible with the fiber core size, because we'll be giving the fiber as an input to a optical receiver. So the fiber core and the receiver dimension should be compatible, and the responsivity at desired wavelength, you should have high responsivity at desired wavelength and low responsivity elsewhere. This is nothing but the selection of the desired wavelength. Okay, our input signal will be traveling at a particular wavelength, so the receiver should have high responsivity at that particular wavelength, and it should be rejecting the other wavelength. That is, it should have low responsivity towards the undesired wavelength. Then it should have low noise and high gain, which is a requirement for every system, and it should be insensitive to temperature variations, and it should have long operation life, and it should be cost effective, and the power consumed should be less, and should be operating at lower voltages. So these requirements are best met by photodetectors made of semiconductor materials. Okay, so when analyzing all these performance criteria, it was found that the photodetectors which are made of semiconductor material exhibit all these properties. So as already discussed in an optical receiver, the main component is an optical detector, and the function of the optical detector is to convert the light signal into electric signal. So how, based on how this light is being converted into electric signal, and the principle that is being followed by the optical detector, the optical detector comes in three categories. One is photoconductive, the other one is photovoltaic, and the last one is photoemissive. Okay, in photoconductive, we have the incoming light, and this incoming light produces free electrons, and this free electrons can carry electrical current. Okay, so we have the incoming light. These incoming light produces free electrons that can carry electrical current. So the electrical conductivity of the detector material changes as a function of light, incident light. That is, as the intensity of the light increases, more electrons, which has the capability to carry electrical current, increases. So as the intensity of the light increases, the electrical conductivity of the detector material changes, because more electrons, free electrons, which can carry the electrical current, is being produced. Okay, so these photoconductive detectors are fabricated from semiconductor materials, especially silica. Okay, so we have incoming light. Based on the incoming light, free electrons which can carry the electric current is increased. That means electrical conductivity of the detector material is being increased as a function of the incident light, the intensity of the incident light. So this is a principle in photoconductive optical detectors. Next, in photovoltaic. In photovoltaic, we are using semiconductor materials in which we have one type of semiconductor where electrons or holes, either of them will be a majority carrier. On the other side, similarly, electrons or holes will be the majority carriers. So these two semiconductor materials are fused, that will produce a potential barrier. So when the light is incident on this semiconductor material, no, basically on the exactly on the potential barrier junction, there will be a voltage drop. So there will be a voltage drop developed, because as the light is being incident, free electrons or holes are produced, so there will be a voltage drop. So if you are connecting a reverse bias or a voltage drop or a load material, this voltage can be generated to converted to electrical signal. So based on the intensity of light, more electrons and holes are produced, more potential is being developed at the potential barrier. If a load is applied across that potential barrier, the electric current flows. Okay. The next one is photoemissive. In photoemissive, when the light falls on the semiconductor material, so on the surface of this for semiconductor material, free electrons are generated. If you collect these free electrons in an external circuit, the corresponding electric current is being generated. Okay, so these are the three basic mechanisms by which optical signal is converted to electrical signal, and based on the principle which is being followed by the optical detector, the optical detector comes under any of these three categories. So the most commonly used photodetectors are one, pin photodiodes, and the second one, avalanche photodiodes. So the pin photodiode and an avalanche photodiode, both are the categories, subcategories of photodiode. So first we'll learn about what is a photodiode, and then we'll go to what is pin photodiode and avalanche photodiode. Okay. So this photodiode is a two-terminal device. As you can see from the figure, it is a two-terminal device. The function of the photodiode is to convert the the light signal into electric signal, and the photodiode always operates in the reverse bias condition. In the forward bias condition, it just acts as a normal PN junction diode, and the p-type material is the anode and the n-type material is the cathode. Okay, so this is the structure of a photodiode. The anode is connected to p-type material, the cathode is connected to n-type material. So in p-type material, the majority carrier is holes and the minority carriers is electrons, as shown here in the figure. And in n-type material, the majority carriers is electrons and the minority carrier is holes. When the p-type material and the n-type material are fused together, there is a space charge region or a depletion region that is being found, that is being developed. How this depletion region or the space charge region is formed is it is like, and the space charge region or the depletion region has a positive ions on the n side and a negative ions on the p side. That is how it came, is that when the majority carriers electrons in the n-type material leave the n-type material, they leave behind a positive or a hole terminal. When they breaks their bond and go to the other side, they leave behind the hole that is denoted by the positive ion. Similarly, when the holes in the p-type flow to the n side, they leave behind an electron, and that is shown by the negative ion. Okay, and one more thing, the covalent bonds in the p side and the n side are very strong compared to the covalent bonds in the space charge region. Okay, so when the light falls on this depletion region, free electrons and holes are generated, and free electrons and holes are generated. This is how, because the covalent bond in the depletion region is of less strength, so it is easy to break the bond in the depletion region. As a result, free electrons and holes are generated. Because of these free electrons and holes, the current flows, and this current is proportional to the light that is incident on the space charge region or the depletion region. And one more thing, the photodiode is always working in the reverse bias condition. Why in the reverse bias condition? Because in reverse bias condition, the depletion width increases, there are more ions in the depletion region, and if more light is being concentrated on a large depletion region, we get large current flowing through it. Okay, so the photodiode is always working in the reverse bias condition. So when you are considering the characteristics of a photodiode, it will be further clear why we are always using the photodiode in the reverse bias condition and not in the forward bias condition. So when this photodiode is connected in the forward bias condition, that is, the anode is connected to the positive terminal and the cathode is connected to the negative terminal, the depletion width will be less, there will be current flowing through it. The current flowing through the forward bias condition will be in the terms of milliamps, and current due to light will be in the range of microampere. Why in microampere? Because the depletion width is less, only a less amount of light is entering the semiconductor material. Okay, so the relative current due to light is negligible, hence we don't that is the main condition, the criteria why we are not using photodiode in the forward bias condition. Because when it is using in the reverse bias condition, you can see first graph is the current flowing through the photodiode when no light and when no light falls on the depletion region, and that current corresponding to no light is called the dark current. Okay, that is highlighted in the orange color of the graph. So as more and more light, the next the blue figure shows when certain amount of light is increased, so you can see a higher current flows. So as we from the graph we can see, as we increase the intensity of the light, the current that is being flowing through the photodiode increases. Okay, so the relative increase in the current is in the range of microamperes when compared to the forward bias condition, which was in milliampere. Okay, so and also in photodiode, when it is in reverse bias, we have a higher depletion width than in forward bias condition. If it is having a higher depletion width, that means more light can be concentrated onto the semiconductor material, which means more current. So the photodiode is always operated in the reverse bias condition.